to introduce to you Dmitrii, who is talking about wildcard logic languages, and this is joint work with Daniil and Petr. And yeah, Dmitrii, the stage is yours, so please start your presentation.
Hello. I hope my slides are changing right, and now you can see the second slide. And my talk is about wildcard logic variables. And to start, I want to ask you to remember a paper from 10 years ago about generating lines in miniKanren. There we have in scheme a relational interpreter that investigates the values of our current expression using pattern matching or condiv unifications. And there are various kinds of expressions in a language, like quote expressions with one argument, lists, applications, and lambda abstractions, and so on. And I would like to pose a question how we say in miniKanren that some logic variable q, which should represent an expression, is not a quote expression, meaning it is not a list that starts from a quote. And we could easily express this in miniKanren scheme. We just say that q is not a quote, and we substitute instead of a whole after the quote a fresh variable, and it works. And it is possible to do because in scheme we have a specific data representation where we specify the arity of the list first, and then we fill the contents of the list. But not every miniKanren implementation do this. For example, we are working on OCanren, which is typed embedding of relational language into OCaml. And there we are designing our data types and values using algebraic data types. Very much simplified algebraic data type is on the left for a language with quotes. And there we have constructors. Constructors define deterministically a number of its arguments and the types of its arguments. So if we want to, and we specify constructor first and arity of arguments later, kind of vice versa comparatively to scheme. And in these circumstances, if I ask a question how we represent the q is not a quote, we could try to write straightforward solution, meaning fresh v, that q is not quote of v, but it will not be a thing that we wanted to say. We said that exists a v such that q is not a quote of this v, but we wanted to say that q is not a quote v for any possible v. And in other words, we have universal quantifier over v, and for every v, q should not be a quote of this v. And we get this universal quantifier, and miniKanren is not really good with universal quantifiers. There are some work about it, but right now, existential variables are much better to use. And it's not obviously how to express these constraints in circumstances of OCanren and typed language. You may think that is too specific to OCanren. Yeah, kind of. We have everywhere algebraic data types. We design all our data types using most all of them using algebraic data types, and this happens to abstract industries for expressions, for lists, and some other stuff. And this issue happens everywhere in OCanren, not only in relational interpreters. And I think we managed to find an example that will make sense, I hope, both for scheme version of miniKanren and OCaml and OCanren. And this example is about piano numbers. And let's try to think how we describe q's such that they are not triple S of v for any possible v. So S is a suc, next constructor of piano number, and z is a zero. So let's try different piano numbers. Z is fine, it doesn't unify with S. 1 is fine too, again with same reason. 2 is fine again. Again, unification doesn't fail. And 3 doesn't fit. Why it doesn't fit? Because we could substitute z instead of v, and our disequality will be unifiable without any extension of substitution. And it's bad. 3 doesn't fit. 4 doesn't fit too. And 5, and again, and again, and again, etc. What we describe there, we describe a single constraint that says that our piano numbers is less than 3. And previously, in various miniKanren implementations, we were able to specify only that piano number is greater than 3 using unification and a few constructors and whole with fresh logic variable. And it's kind of cool. And the main contribution of our work is our wildcard logic variables, which allow us to specify exactly this kind of constraints about piano numbers and, in general, more interesting examples. We are also applying our work to OCanren and add more expressivity to it, some more details about it later. And we are working on application of this stuff to pattern matching synthesis. So if you want to repeat our work and create implementation sketch, what should you do? Well, the first, we introduce wildcard logic variables. We denote them as 2 underscores, because single underscore is kind of specific to OCaml, has special meaning. And to do this, we modify unification in the following manner. Wildcards unify with everything, but during this unification, they do not enrich a substitution at all. They keep substitution the same. And for simplest case, you could leave disequality constraints implementation as they are and do not change them. Let's look at a few examples how this may work. In scheme, let's try to unify 2 pairs. First pair will be number 1. Another element of the pair will be a fresh logic variable 10. And we want to say that it's not equal to a pair where first element is wildcard and second element is number 2. 2 pairs are not equal when either first elements are not equal or second elements are not equal. First elements are number 1 and wildcard, and we expect them to be not equal for any filling of wildcard. And let's suppose about the worst case scenario and replace wildcard by number 1. And now first elements are kind of equal, and they couldn't be not equal, meaning that disequality of pairs could be simplified to disequality of each second components. Another example is disequality that follows unification. We have a disequality between a fresh logic variable 10, and it should be not equal a pair of 2 wildcards. And we later say that this logic variable 10 is unifiable with a pair of 2 fresh logic variables. For example, we are going to check the constraints. We basically should do unification between one logic variable 11 with wildcard and second logical variable in and wildcard. Unification between wildcard and everything doesn't extend the substitution. It means that disequality checker will perform unification. It will get a success and substitution will not be extended. It means that these 2 values are already equal without any extension of substitution, and this disequality will fail. The most interesting and complicated case is disequality between wildcard and fresh logic variable. And this is complex because it requires us to speak about the domain of fresh logic variable. For minimal implementation, you could safely assume that existential logic variables have non-empty domain, which means there is a citizen of this domain, and we could substitute it instead of disequality in 2 places and get disequality violated. But for logic variables with empty domain, these disequalities should simplify to success, meaning this disequality could be removed. So there are a few related works. The most famous one probably is about agent variables. where the authors use them combined with unification of fresh logic variables to synthesize some relation interpreters about SKE calculus. And in this work, disequality constraints are not required and not used because they are not needed for the task. And eigenvariables are intermixed with only fresh logic variables. Our work has designed wildcard logic variables to be used exactly in disequalities and not in the unifications. So these approaches are not directly supersede each other or vice versa. Another promising approach to universal quantification is a recent paper from previous miniKanren workshop a year ago, and we studied it a little bit, and we got an feeling that it requires some more polishing to be applied to our tasks. So we decided to work on our implementation. And one more application of our approach is its application to OCanren. Well, miniKanren is a domain-specific language, and every domain-specific languages have some issues. Meaning, for example, you can't take a random scheme programmer, give him a miniKanren, and he will be very fast. Not really a random scheme programmer, experienced scheme programmer. You can't expect from experienced scheme programmer to become very fast, powerful with miniKanren. Learning DSLs requires some study. And there is an idea to synthesize relational code from general purpose language. In our case, it is OCaml. And this is a joint work of Petr Lozov, who will be the first presenter today, and other colleagues in our group. And if you do this, actually we did it, and we get type checker from OCaml from free. We have convenient OCaml-like syntax for free, and we have a pen and paper proof about semantics preserving transformation that says that synthesized program gives expected results. But in this work, there are some restrictions of this subset of OCaml, which we, by tradition, call convention in OCaml world ML world Kosarev Lozov ML, and these restrictions are quite strong, really. Well, we have some best practices about programming languages, and in this approach, we write some OCaml-like code, but best practices of OCaml could really hurt performance, because the semantics is a transformation, it's not really OCaml. And some language features are not available, which is bad, like pattern matching guards. And some other features are not available too, like overlapping patterns append. We need to manually blow up our pattern matching and increase the amount of code to write something. And we think that using wildcard variables, we could overcome the last shortcoming about overlapping patterns. Let's try to think what could possibly go wrong with it. On the left, you see a pattern matching of two Boolean values with two patterns, which are overlapping. And we could try to write a straightforward translation to OCanren. Straightforward meaning we don't have any disequality constraints or direct constraints except unification. And we have two branches. We have cand_d. Cand_d has two branches again. And in pattern matching, if you try a pattern and it fits, we continue execution in the right-hand side. And we do not check the next branches. But in cand_d, these branches are independent, and this condition of try first and don't try the next ones is not implemented in this cand_d. So the straightforward encoding could give us more answers that we expect. For example, if we write a scrutiny which is a true and fresh logic variable, we could both have values 1 and 2 in the res logic variable after execution of this relation. We could try to repair it using disequality constraints, but it's not finite solution because these disequality constraints have some existential holes in it. You can hear which we write true instead of true and write existential fresh logic variable instead of wildcard. And there is the same problem as the example in the beginning, that this constraint doesn't constrain anything. And we still get 1 and 2 as a result for scrutiny, which is true and logic variable. And we also try to implement wildcard logic variables where we use our wildcard logic variables instead of wildcards. And it helps in this problem. We have, for a pair of true and logic variable, we will get only one answer because this unification with this scrutiny will fail and second branch of candi will not be executed. And idea is to encode in pattern matching positive and negative information. We encode positive information of the branch using unification, and we encode negative information using disequalities and wildcards, meaning that all previous branches will get a distinct disequality constraint, where wildcards will be replaced by wildcard logic variables. And another work in progress application of our stuff is application to pattern matching synthesis. We had a paper about this 2 years ago. A small reminder about what is happening there. And we have input language. In input language, we have algebraic values with constructors and arguments. And we have pattern matching with patterns and constructor patterns and wildcard patterns. And let's say we have some semantics that gives for every V and every patterns and index of the branch where execution should continue. And we want to compile this input language into intermediate representation, compiled representation, where we do not have any pattern matching, but for simplicity, we have if expression that checks that scrutiny or part of scrutiny starts with specific constructor. And we pose a synthesis task that says that for every possible scrutinies, our two semantics of compiled representation and pattern matching should behave the same, meaning for every scrutiny should give the same branch index. And as you can see, there is a universal quantifier here. And miniKanren is not really good in universal quantifiers. But there are a few observations which allow us to replace this universal quantifier by a finite conjunction. If we know the type of scrutiny, we know the shape of all algebraic values that will be matched. And for every concrete pattern matching, we know the depth of the patterns. We could see that concrete pattern matching doesn't look into scrutiny too deep. And we could replace this universal quantifier by a finite conjunction of ground examples of scrutinies, which is kind of good. We will not have a finite universal quantifier and synthesis will perform somehow. But the bad thing is that exponential blow up of these examples and everything is very slow. And our long-term plan is to somehow overcome this issue, replace a universal quantifier by something smaller, and we're going to have a better performing synthesis process. And we tried to apply our wildcard logic variables to this task, and we have basically the same idea that we have with OCanren. We encode positive information with unification, negative information about previous branches with disequality constraints, and ban some bad behaviors using these wildcards and disequality constraints. And we were kind of optimistic about that, but in practice, wildcards are not enough to overcome the exponential blow up, because previously we had everywhere ground examples, exponential number of ground examples, And there in positive information, we have existential holes in our scrutiny, which allow synthesizer and relational interpreter to investigate non-expected parts of scrutiny and generate, formally speaking, correct, but answers that we do not expect. And answers which are considered right appear later, but they appear very late, and the performance is very slow. And it means basically that we have faced the complication that was not appeared before about existential holes in examples, and previously all examples were ground. Basically, it means that wildcards should be useful in the same manner as in OCanren, but we probably need something else to finish our synthesis and improve it. So the main results is ability to express that piano numbers are less than a constant, and we do this using wildcard logic variables. And we applied these to OCanren and achieved some more expressivity about the language that is being translated to relational OCanren. And we have a work in progress application of this to pattern matching synthesis. And if you have some ideas how to encode and improve this, we will be glad to hear your ideas. And this, I have some extra slides, but it's probably not time to say them, and I should finish.